it's easy enough to see that the kinetic energy of the car near the bottom of its motion is being converted on the way up into potential energy. And is all potential energy at the top of the path. The potential energy now converts back into kinetic energy, and at the bottom there it's all energy of motion. The same kind of thing is happening here. Watch it in slow motion. Kinetic energy, the energy of motion, now becomes the energy of separation between the ball and the earth. And down at the bottom, it all goes into potential energy of compression. Now all along, all the time, the ball is losing energy. What about the principle of conservation of energy? You know it loses some by friction with the air, but it also loses some when it hits the glass plate. It's a lot easier to photograph the compression of a rubber ball than a ball bearing, but the idea is the same. As you can see, the energy loss at impact is important, but it's easier to discuss the energy loss due to friction with the air, and once you've understood that, you'll understand the effect at the solid surface too. Let's go take a look at a model of a gas we've got over here. First I'll drop in one molecule, and now I'll add another, and now another. And even with only 3, you see how ridiculous it would be to try to keep all these motions in mind. Even in slow motion, even though it's easier to see, you'd still have to be outrageously patient to keep track of all of these motions. But with enough molecules, this motion, this chaotic motion, takes on a certain kind of order. We'll use this barrier for a piston. The effect of the impacts of many molecules tends to average out, and we see a smoothing effect. Now, in a real gas, we substitute average quantities. For instance, for the bouncing of the molecules against the wall, for the collisions that impact against the wall, we take an average quantity called the pressure, the force per unit of area. You read it on a pressure gauge like this. And for the motions of the molecules inside the gas, what we do is to substitute for their average kinetic energy of motion, average kinetic energy of linear motion, a simple quantity called the temperature. You know, what you read on a thermometer. Now, what gives us the privilege of substituting a concept like temperature for the average kinetic energy of motion of the molecules? Temperature you've grown up with all your life, and the kinetic energy of a molecule is something that maybe you just hear about. The argument is really simple. It goes something like this. The kinetic theory of gases, the theory, says that the pressure in a gas is proportional to the average kinetic energy of the molecules. The average kinetic energy of the linear motion of the molecules. The text has it all worked out, but let's write it this way. One of these quantities, mv, comes from the momentum change at impact. The molecule hits and it bounces back, and the momentum change is, of course, proportional to the momentum of the molecule. And the other v comes in because the faster the molecules are going, the more molecules hit the wall. That's easy enough, and that's why we get the mv squared. Now, experiments say that the pressure in a gas is proportional to the absolute temperature. the pressure is proportional to the absolute temperature. This is a little more complicated than I make out here, simply because we use this relation to define absolute temperature. In order to clarify this notion, let's go do some experiments over here. We're going to observe the pressure of a gas as a function of the temperature. Here we have a container with 2 atmospheres of helium gas. Andy, would you take this? We're going to immerse it first in boiling water, then in melting ice, then in dry ice and alcohol, and finally in a bath of liquid nitrogen. Okay, Andy, can we start taking some readings?
.49. 1.81. 1.38. 0.55.
Now let's take a look at the pressure readings. They go all the way from above 2 atmospheres, from 2.5 atmospheres, all the way down to half an atmosphere at the temperature of liquid nitrogen. So let's try the experiment again with another gas. This time we'll pick oxygen. Okay, Andy, let's go.
.43. 1.81. 1.39. 0.31.
Let's take a look at the oxygen data. Compare the 2 sets of readings. Remember, we forced them to fit at room temperature at 2 atmospheres for both. But at boiling water temperature, and at melting ice, and at the dry ice temperature, they agree perfectly, as well as we could read them. But down here at the temperature of liquid nitrogen, the oxygen reading is very different from the helium reading. Some of you may have guessed already what went wrong there. Let's take a look here. Here's some liquid nitrogen in a tin can, and let me hold this so you can see. You can see the oxygen from the air condensing on the outside, and if you don't believe that's oxygen, just watch what happens. So you see what happened in the experiment is that the oxygen partly liquefied in the bulb. If we had taken a lot less gas, for instance, if we had put in less than 1/10 of an atmosphere in both bulbs, then the readings would have agreed all the way down, right down through the nitrogen point. What I'm trying to say is this, that for gases that are thin or tenuous, like the gases in the upper atmosphere, if the agree at one temperature, if you take a certain amount of gas so that they agree at one temperature, they will agree all the way up and down. So we take this universal property of gases, as a way of defining the temperature scale. In order to clarify that, let's go look at the graph right here. Let's plot the pressure against temperature, but we've got to pick a temperature scale. Let's set the temperature of melting ice at 273 degrees arbitrarily, and we put our point there. Now what we do is to draw a straight line right through that point and the origin. Then we can put our other data on that graph and say, by definition, that the pressure is proportional to the temperature. And that defines our temperature scale. Now, if we want to read the temperature of boiling water, say, we put its pressure at 248 right there and read its temperature. It comes out, of course, 373 degrees. That gives us 100 degrees between the temperature of melting ice and the temperature of boiling water. And that's exactly why we chose the 273 for the ice point. So we'd get that 100 degrees difference between those two temperatures. Now, if we want to find the temperature of the carbon dioxide slush, we plot its pressure at 1.4 right there. So it comes out 220 degrees absolute, and the liquid nitrogen temperature, the pressure from the helium graph, of course, we put right at 0.55 there. So it is at a temperature of about 80 degrees absolute. Now let's plot the oxygen point here. That 0.29 falls off the graph. You knew it would. And you know why? We started with too much gas in both of the bulbs. Too much helium, too much oxygen. They weren't tenuous enough for them to agree all the way up and down. Let's go back to the logic. What we said was simply this. From the theory, from the kinetic theory of gases, the pressure is proportional to the average kinetic energy of linear motion of the molecules. And we've just discussed that the pressure in a gas is proportional to the absolute temperature. We simply identify one with the other and say that T, the temperature, is proportional to the average kinetic energy of motion of the molecules. We simply measure the average kinetic energy of translation of the molecules by observing the absolute temperature. When a gas is hot, the molecules are moving fast. When it's cold, the molecules are moving slowly. But all of that energy is chaotic. It's random. Now, in a mixture of gases, with heavy molecules and light molecules, the heavy ones are moving relatively slowly, and the light ones are moving fast to keep their kinetic energy up. Even in the extreme case of these particles of smoke, in this Brownian motion experiment, the average kinetic energy of the smoke particles is the same as the average kinetic energy of the molecules of the air, even though these smoke particles contain millions of atoms. Okay, let's get back to our original question. What happened to the bouncing ball when it lost energy to the gas? In order to show what we think happened, we'll have a model. Here's a frictionless disk, which we'll let slide down an incline, gaining kinetic energy as it goes until it hits. Now, what would happen to that if it went through some gas? The best way to show that is to bring on some gas. And the disk comes to a Brownian motion halt. Let's try it again. The orderly kinetic energy of the disk is transferred into disorderly random motion of what we have called the molecules that were hitting it. It may not be perfectly apparent, but every time a molecule hit that disk, some of the energy of the disk was transferred over to it. In that way, the disk lost its energy to that gas of molecules. In exactly the same way, when this falling ball that we were talking about falls through the air, its energy is transferred into the random energy of motion of the gas, random energy of motion of the air. And when that ball hit the table, hit the plate, then the same sort of thing happened. The orderly energy that you could see, both potential energy and kinetic energy, were converted over into energy of motion of the molecules, of the plate, and of the ball, and of some of the air. So we have to ask the question, is the energy conserved? It certainly is. Then where does it go? At least you know what it doesn't do. It doesn't just go backwards like this. What usually happens is that we get what we call thermal conduction, heat flow. Energy flows from a hot body to a cold one. Let's go take a look at a model of that over here. Here is our old friend, the marble machine. Let me turn it on first. The marbles in the lower compartment have no effect on the ones in the upper compartment. They are separated by two bars with an insulating airspace between them. Now suppose we take away that insulating barrier. It's a little clumsy, but let me try it. Right, just like that. With the insulating barrier removed, the marbles in the lower compartment are now able to transfer their random thermal energy to the marbles in the upper compartment. And that's exactly what happens when we heat something with a flame. Here's a flame, here's something, bulb of gas, and the molecules in the flame that are moving very rapidly transfer their kinetic energy first to the bulb, and then to the gas. Now, some of the energy of the flame goes into the energy of the gas, and the temperature goes up, and the pressure goes up. Now, what do we mean by the principle of conservation of energy? Energy appears in various forms as kinetic energy and potential energy, and sometimes it's orderly, and sometimes it's random. And when it's random enough, we call it thermal energy. Some people call it heat. What we mean by the principle of conservation of energy, then, is simply this. We believe that energy is never created, never destroyed. We may convert it from one form to another, from orderly motion to random motion. We may fritter it away by warming up the air, by warming up the ocean. But it's still somewhere. Now, there's one more thing we've got to discuss before we finish. Now, when we transport energy, we might transport the whole material body, complete with the energy and all, like throwing hot rivets or carrying coal. Or we might have energy transported by molecular bombardment. We've just been discussing that. We call it heat conduction. Or energy might be transported by radiation. Usually this takes the form of electromagnetic radiation, say infrared light or visible light. In fact, most of our energy comes to us that way. It comes to us from a star, our own personal star called the sun. In the sun, the energy is stored by the atomic nuclei. And this energy is converted into random thermal energy in the sun, and that random thermal energy into radiation. And the radiation comes through space, and some of it is captured here on the Earth. And some of that, by the process of photosynthesis, is converted into trees. And the trees were converted into coal or oil. And some of that fuel was converted into hot steam, or something that turns a turbine, or runs a motor. And we get orderly mechanical energy out of that. But regarding the conversion of thermal energy into mechanical energy, and then mechanical energy back into thermal, more of that in the next film.